Okay, so for this particular lesson, properties of exponents and scientific notation, I'm going to split it up into two separate videos, okay? So first we'll start off with the laws of exponents, okay? Or properties of exponents as they are called in this section. Usually they'll go by the term laws, right? So laws of exponents. And so let me kind of list those out, okay? So first of all, we have if you have something raised to a power times that same base number, but raised to another power, then what you could do is simplify it by writing it one time with the two exponents added together. Okay, so that's the first and most common law of exponents. Okay. The second one that we'll talk about is if you decide to do the same thing, but instead of multiplying, you decide to divide them, then you can simplify it by subtracting the exponents, a minus b. Okay, and again, these are all numbers or a mixture of numbers and variables. Okay, if you happen to have x to the a power raised to the power of b, so what you're doing here is you're raising an exponent, or you're raising a term with an exponent to another exponent. You can simplify that by writing it once and multiplying the two exponents together. Okay, those are the main ones there. We could also talk about what happens if you have a negative exponent. Okay, that actually just means find the reciprocal. Okay, that just means kind of move the position. So this is can be thought of as, that over 1. Well, the negative exponent just means now it's going to be x to the positive a power in the denominator. Okay, 1 over x to the negative a. Okay, this is just the same thing, basically. If you end up with a negative in the a negative exponent in the denominator, then you can actually just rewrite it in the numerator, okay? You just move it. All right, and then finally, one more I want to mention, and that would be x to the 0 power. Anytime you have anything to the 0 power, it equals 1. Okay, so these are just ways to simplify expressions, okay? Make them a little bit neater and easier to work with. Okay, so let's go on to some examples. So our first example here, we have y to the 3rd power times y to the 5th power. Now that by itself is kind of a bigger expression. I could rewrite that in a nicer form as y to the 8th power, where I just simply added the two exponents together. Okay, what if I had x to the 5th power divided by x to the 4th power? Okay, looks like this one here, right? It's division, so that means subtract the two exponents. 5 minus 4 is 1. Okay, well, that 1 is understood, so I'll just leave it off. It's just x. What about 6z to the negative 8th power? Okay, there's my negative exponent. Okay, well, negative exponents means to put that term in the denominator. So be careful, though. This 6 actually has its own exponent, right? It has an exponent of a positive 1. So we're not going to move the 6, just the z. So this ends up being 6 over z to the positive 8th. Okay, so make sure you make that exponent positive. Okay, what about 5x to the 0 power? Okay, remember that 5 has its own exponent of 1. That x to the 0 power is going to turn into 1. So this is 5 times 1, and that's just 5. Okay, so not too bad. Let's kind of complicate these a little bit. Example 5. Here's x to the 5th power over x to the negative 4th. The reason why this one's a little complicated is because now I have this negative exponent that I'm going to have to deal with while I'm trying to simplify the overall problem. Okay, well, remember, if you divide them, you can subtract those exponents. So the top exponent minus the bottom exponent. And that's going to actually take care of my negative on its own. So minus a negative means plus, right? This is really just a plus. And so 5 plus 4 is 9. So I can write this as x to the 9th. Okay, see how I cleaned it up a good bit. Okay, what about n to the 4th power over n to the 11th power? Well, again, remember the rule is to subtract the exponents, but when I subtract 4 minus 11, I get a negative 7. So now I have a negative exponent, and that's something that Hawks considers to be improper, okay, at least when it deals with these types of problems. So we don't want a negative exponent. We need to rewrite this. Remember, the negative exponent just means bring it to the denominator, or if it's already in the denominator, bring it to the numerator, and then you can change it to positive. Okay, I'm not go too far down here. Okay, example 7. N to the 6th power times n to the 3rd power over n to the 5th power. All right, got a lot going on here. Now I can break this up into 2 pieces, or I can do it all at once. And I think I'm gonna do it all at once. Okay, remember, first of all, these all have the same base, right? So they can all go together. Remember, when you multiply, you add the exponents. So in this case, the multiplication gives me addition. But if you divide, like we divide by this term here, you subtract. So I'm going to subtract 5. So that's 6 plus 3 minus 5. We can all do that, right? That's 4. So this is n to the 4th. Okay, let's complicate it some more. Okay, so here we are raising our expression to an exponent, a power of 2. So we can actually take care of this in either order. We can deal with the inside first and then deal with the outside, or we can do it the other way around. I think we'll just deal with the inside first. I think that's probably easier in this case. Okay, maybe later we'll deal with the outside. I don't know. We'll see. Okay, so 2ab to the negative 3rd. Now, none of these have the same base, so I can't go and try to merge their exponents together. But what I can do is take care of the fact that this b has a negative exponent, so I can bring it up top. Okay, so then all that's left in the denominator would be an understood 1, so I don't have to even write it anymore. So this becomes 2ab to the 3rd power, all raised to the 2nd power. All right, so there we go. 2ab to the 3rd, all raised to the 2nd power. So then what happens there? Remember what the rule is. If you have an exponent sitting on the outside, that means multiply that 2 by the exponents on the inside. I don't see a bunch of exponents, but I know there's an understood 1 right here. There's an understood 1 right here. And then, of course, we have 3 right there. And so I'm going to multiply all of those by 2. So 1 times 2 is 2, 1 times 2 is 2, 3 times 2 is 6. Oh, but I can simplify that even further, right? Because we know what 2 squared is. That's 4. And so this simplifies to be 4a squared b to the 6th. Okay, let's do another similar problem. Okay, similar to the last one. Big difference here, though, is that I have 2 terms at least that have the same base, so I can actually merge those 2 together by subtracting the exponents. So let me do that. That's going to give me 2a to the 3rd power b to the This is negative 2 minus 3. Negative 2 minus 3 is negative 5. Okay, raise to the third power. Now let me multiply all the exponents, including the understood exponents, by 3. All right, let's take care of this 3. You can think about it kind of like distributing, right? It's kind of the same thing. Okay, and so now let's see if I can simplify that any further. And of course I can. 2 to the third power is 8. A to the ninth is fine. B to the negative 15th, can't have that, so I bump B to the denominator and make the exponent positive. Okay, here's probably the ugliest problem, so let's do that. Ugly problems are kind of fun sometimes. Okay, y to the negative 6th times y to the negative 4th, z to the negative 3rd, raised to the second power. Just kidding, that's not all. All over 3 times y to the negative 2nd, raised to the 4th power, z to the negative 8th. Okay, fun times, right? So what I'm going to do is, well, there's a lot of different ways you can start this problem off, but I think because of the fact that it's not all raised to a single power, right, but it's only certain pieces, like that's raised to the second power, and this is raised to the 4th, I'm going to deal with that first. Remember, that just means multiply the exponents. Okay, so y to the negative 6 stays the same. Negative 4 times 2 is going to be a negative 8. Negative 3 times 2 is a negative 6. 3 stays the same. Negative 2 times 4 is negative 8. And then z negative 8. Okay, so now I'll see if I can combine some things. For example, I see these 3 right here all have the same base, so I can work with that. Now, of course, I can do y to the negative 6 minus 8 plus, well, minus negative 8, right? I could do that. And there's nothing wrong with doing that. However, let me point out something. Aren't these two the same thing? Yeah, they cancel each other out. So that actually kind of worked out a little nicely there. We have y to the negative 6. For z, remember you're going to subtract those exponents. And see what happens there. And 3 is actually fine. We can just leave it alone. It has a positive exponent, right? An understood 1, so it can stay down there. Okay, this is really an addition, so negative 6 plus 8 is 2. So we have y to the negative 6, z squared over 3. Okay, so we're still cleaning this up. And then this y to the negative 6 can be bumped down to the bottom to take care of that negative exponent. So we are left with z squared over 3y to the 6th. All right. Now here are a few other problems. They look a little strange, but I want you to see that they're the same thing that we've just done. Okay, so let's talk about them. 5 to the 4th power. Okay, what does that mean? That means 5 times itself 4 times. All right, that's just 5 times 5 times 5 times 5. All right, so you can type that in a calculator, or you can think that through different ways. That's 625. How did I figure that out? Okay, well, I know that's 25. Oof, that's ugly. And I know that that's 25. And if I multiply 25 and 25, it equals 625. Okay, so there's just different ways you can do it. Another way to think about it, not the way I saw it, but this works. This is 125 times 5, and if you go 125 5 times, you get 625. Okay, well, whatever. Or just type it in the calculator. Don't really care. 625. This is where I'm trying to get. I want to compare number 12, which is, I said number. Let me put example in front of these. If you look back at that, you can tell these are examples. I'm not just putting numbers down. Okay, have I been doing that? Yeah. Okay, so I want to compare example 12 and example 13. They look the same, but they are not the same. Okay, so let me give you what these actually represent. This one means -1 to the first power times 5 to the first power raised to the fourth power. This one means -1 to the first power times 5 to the fourth power. Okay, they mean something different. So what happens to the top one? You multiply the exponents. Understanding that a negative multiplied by itself an even number of times cancels out the negative and leaves you just a +1. So this basically is non-existent. It's just a +1. And so I'm left with +625. What happens here? Well, -1 stays. 5 to the fourth power is 625. This one gives me a -625. Okay, so you see the parentheses make a difference. The negative here occurs 4 times, and therefore it cancels out. The negative here is not attached to this exponent 4, and so it does not cancel out. All right, last example. (7 to the -4th power over 7 to the -8th power. Okay, remember the rule. You just subtract those exponents. This is really addition, so -4 plus 8 is 4. So this is really 7 to the 4th power. And here I actually will get a calculator out. 7 to the 4th power is 2,401. All right, 7 times 7 times 7 times 7 is 2,401. Okay, so there we go. Those are the laws of exponents and some applications of those laws.